Now I'll cover methods of superposition, where you can actually take advantage of solving each problem separately and then adding them up to take advantage of that. Superposition when things are linear and you can actually add them up. So here in this case, I am going to take this problem here. Looks very complicated, has a distributed load and another load, a point D. But rather than looking at that problem, right, looking at that problem as a whole, what I want to do is break it up into two. I can solve this problem first and then solve this problem separately and then add them up. And you will agree with me that solving that problem here, number one and number two, should be very feasible because I actually kind of did it in the previous examples. So all you have to do is add the solutions up and then you can get the deflection of the beam due to that superposition. Is that clear? I'm not going to cover into extensive details on how to do it, but let me show you an example problem at the very top level. I'm not going to go into the details of that because the whole point was to showcase what superposition moment here. So here, let me give you this problem here. So in this problem, you're applying distributed load only on the right-hand side, not on the whole beam. So what you could do for this example problem, you could convert the problem into two. So you have the problem here. You have this problem, and we can break it up into this problem with loads applied downwards and subtract the load going upwards. Solve this problem and solve this problem separately using deflection theory, and just add this deflection to this deflection to get the total deflection. That's one way to do the problem. And the way I'm showcasing this one is because a lot of books do have the solution for this one, do have the solution for this one, and then you can then add them up to get other solutions that you may not have in that table. Bottom line is you can superimpose solutions as long as the problem is linear and you're staying within a linear elastic regime of the structure. These exactly came out straight from books that have that solution. So I have the solution for this distributed load, tells me what slope I get at point B. It tells me what deflection I get at point B. For loading number two, which is here at the bottom, I also can get from a book of tables that have that solution. And sorry, this is a point C, not a point B. But I can actually extrapolate what will be a point B because there's no load applied here. So this is going to kind of follow linear. This is going to be extremely like line. It'll be like a line. So you can actually extrapolate what the deflection, the slope will be the same. The slope should be the same at point C and point B because there's no load applied between point B and C. But on top of that, if you know how much you moved at point C, you will know how much you moved at point B because it's a linear, it's like a triangle. So there's no curvature, right? There's no load applied, there's no curvature. So you expect it to be extremely like a line, basically a line. So therefore, you can project what deflection will be at point B. You know the deflection at point B here from loading A, but 1 and from loading 2. You can add them up to get the total deflection for that problem. And I did it here. Take a look. It's just another application of how you could do this in a visual way. That's another thing I like about this. You can do it visually, break up the problem into simpler things to look at. Maybe there's a table that has equations, but you can then add them up and not have to go through the suffering and pain of deriving all the equations one by one. Is this really needed for every problem? Not really. You can solve it without that. But here's a technique that can be helpful to you if you solve it. Yeah, so there you go. Here's another problem. That's application superposition for indeterminate beams. So say that this here was fixed, like pinned. I can remove that pin and apply a load. So that you can break this problem into two now. You can break it up so that it's deflecting downwards. You apply a reaction force going upwards. And the superposition, this one and this one, needs to give you a deflection at this point at 0. So it's a little trick again, where I removed the pin support that was here, removed it, put the reaction force, converted this problem into two. One where I have a distributed load and one with the reaction force alone acting upwards. Get the deflection curve for this one, get the deflection curve for this one, add them up, and make sure that point B, you get 0 as the deflection. And when you do that, it actually allows you to solve for that reaction force and solve it in the indeterminate system. So there's many different ways to solve this kind of problem. I already did an indeterminate analysis earlier for you. I'm just showing you just yet another way of doing it using this technique, superposition. Very powerful technique. And I'm not covering the bullet points explained here because I said it verbally to you. But if you want, and you're at home and you want to review this, pause the video, read this. But I think my words make sense or not? They make sense? Great. So why we don't provide another example so that things are becoming part of who you are, which probably you don't want to become like a bean, but you get what I'm saying. Here is indeterminate system. Pin, pin, pin. That's 3 pins. So, sorry, 2 rollers and a pin. That's a lot of reaction forces. So how you do with that? Break up the problem. So I took the point B and converted that to a RB, like a reaction force at RB. And so I treated this problem into 2. So I divided this into a beam that's simply supported under distributed load W. And then I have a load B reaction force applied at point B. You can actually solve, I already did this problem, by the way, earlier. Not the exact same problem, but very similar problem. I also did this problem also in a very similar way. So all I had to do is get the deflection of the beam for this problem, get the deflection of the beam for this problem, which I'm showing how it looks here at the bottom. And then what you're going to do is you're going to make sure that when you add the deflections from loading 1 and loading 2, that at point B, you get 0 deflection. That's really what you want. And you can see here that I kind of showed you what the solution is. I invite you to try it at home. And when you get the deflection of the distributed load and you superimpose it to the redundant reaction force loading condition, when you add these two, what I want to do, I want to make sure that when I add these 2 deflections at point B, I get 0 deflection, because at that point, you can see I have a roller. There shouldn't be any deflection. So basically the deflection at this point from loading 1 and the deflection at this point in loading 2, if I add those 2 deflections, I should get 0 for the total combined effort. And you can see here that that's exactly what we did. And that allows us to solve for the reaction force, which we couldn't have done if we had not done that step. And now that you have the reaction forces, it's possible to get all other reaction forces. It's possible to get the deflections, and everything else is needed. Okay.